Right, so yes, I'll be talking about Windows drivers attack surface, some new insights. So my name is Ilya. I work for a company called IOActive. I am the director of penetration testing. I do pen test, code review, basically break stuff for fun and profit. And I'm here to talk today about Windows drivers attack surface. It's sort of divided up into, I have a little intro, and then I've got two pieces. And piece one gives you some background and talks about the where. And then part two is sort of the guts of the talk, and it talks about the what. I got a lot of ground to cover today, so I'm going to try and move my way through part one really fast. I hope you'll bear with me. If I don't, I'll run over, so I kind of have to. So yeah, what's this talk about? Basically, I'm going to be talking about the attack surface of Windows WDM, which is the Windows driver model drivers, and specifically about the implementation security. I guess the audience is sort of if you're looking for bugs in Windows drivers, this talk might be interesting. If you're a driver developer, this talk might be interesting. If you're just curious about this kind of security stuff, then this talk might be interesting too. In terms of knowledge, it'd be nice if you have some kind of general background on what an operating kernel looks like, and if you have some specific knowledge about Windows kernel and Windows drivers, that's even better, but not necessarily required. Before I talk about my presentation, it's clear to say that standing on the shoulders of giants. There have been a number of people that have done research in these things, and I would do a disservice if I didn't at least put their names up there. If you think I missed someone, please let me know. I'd like to add their name to it, but I think this is a fairly good list. This talk is slightly different than most of those, though. So if you look at most of the previous research on Windows kernel and Windows drivers, it's mostly been focused on exploitation, and it's usually been focused on the Windows kernel specifically and not so much on drivers. And it's almost always been focused on like one particular issue. And so my presentation is different in the sense that the focus isn't so much on exploitation, but it is more on the identifying of bugs, and then giving some kind of guidance on how would you mitigate or fix these issues. Also, it isn't so much about the Windows kernel itself as it is about specific drivers. Of course, they go hand in hand. You can't really have one without the other. So most of this stuff applies to the Windows kernel as well, and vice versa. But it's a slight difference, though. And the other thing is that I'm not talking about one particular issue. What I did is I sort of sat down and said, looked at all of the common bugs you have or you find in most Windows drivers, and sort of try to find the common theme around it and a thread, and that's basically what I'll be talking about today. Right, so the intro is basically this talk's intro. You could easily spend days talking about all sorts of intricate little details about Windows driver bugs, and so I tried to get it down in the 1 hour thing. And basically it comes down to all of these little obscure things that very few people seem to know about them, and what the consequences are if you know or don't know about little things, or if you do them wrong, or and whether or not that's documented or not. And it turns out some of those things are kind of like, most of it you'll find it on MSDN, but a lot of it is like you have to read between the lines. You'll have these subtle hints as to what is problematic and what isn't, but quite often it's not explicitly mentioned. And so it makes it very hard for people to know these things, and that includes, unfortunately, most driver developers. So with that, let's dive into part one. So yeah, this section is meant by no means to be exhaustive. It's a quick reminder, and I'm going to try to make my way through it really fast. So basically, I'll start off with a little bit of architecture. Basically, at a high level, the Windows kernel is divided up into all of these managers that have their own tasks to do, and the idea is that you as a user, if you want to get to them, you basically call system calls, and then you end up in one of these managers. For example, if you do anti-device I/O control, you end up in the I/O manager. From 50,000 feet view, this is kind of what it looks like. So you have, I don't know if you, no, you don't, okay. Basically, from userland, you call system calls, and then you'll go into your call table, and then it'll go into one of these managers. Quite often, you end up in the I/O manager. Inside this thing, there's a whole bunch of frameworks working together. There's over a dozen, and all of these are worthy of their own presentation. And I wish I could talk about all of them, but due to time constraints, I'm going to limit myself to the Windows driver model, WDM, and a tiny little bit about KMDF. So yeah, what is WDM? It's basically the Windows driver model. It's been around since around Windows 2000. It sort of extends and updates the old NT driver model. It is the standard model for how drivers are written. I mean, in recent years, there's been a shift towards KMDF, but there's still a fair amount of WDM. And so that's why I'll basically focus on WDM. So let me now say a few things about the I/O manager, which is sort of, it's this proxy that sits in between the user and going to drivers. And depending on what kind of request you do, it may or may not do some kind of validation. So it takes your request from userland, and then it sort of packages it up in this thing called an I/O request packet, an ERP, and I'll talk about that in a little bit. And then basically, it finds your driver's dispatch routine for whatever thing you want to do, and sort of hands it off to there. And let me try and illustrate that with some code. So basically, if you have like a very, very simple driver, basically has this thing called a driver entry, which is basically the main entry point. And then essentially, any driver that wants to have interaction with userland goes to the I/O manager and says, hey, create this device. They call I/O create device. And then they say, okay, now that the device is created, I want userland to be able to talk to it. And so they go to the I/O manager and say, I/O create symbolic link, and basically what it does, it creates a symbolic link for userland to talk to that device. And so basically, this means is you register a bunch of dispatch calls to the I/O manager, and then you basically can do ioctls or FS controls or open, read and write, and so forth. In code, this kind of looks like this, where basically, as I mentioned before, you do a create device, create symbolic link, and then you do all of these dispatch functions. And then for all of those functions, you basically have and there's more of these. But basically, for all of these functions, it kind of looks like this, where there's two arguments that get passed along. It's the device object and the actual ERP. And so the ERP is interesting because this contains all of the data that's packaged up from userland that your driver gets access to. And this includes things like data being passed around, your I/O status, what kind of request mode you are, and basically it sort of this kind of nicely completes it where it says, okay, this is the pointers that come from userland. This is the system pointer, user pointer, memory descriptor lists, your ERP stack. And so let's talk about the ERP stack. Basically, for every ERP that comes in, there's a stack associated with it, which is this ERP stack. And it contains very specific information that your driver needs for that particular operation. And so it'll say, okay, you were called with this major minor function number. It's this device object, it's this file object. And then based upon which major minor function number, there's a specific parameter union. And it'll have different sets of elements inside union based upon whether it's ioctl or read or write and so forth. But essentially, all the specific data you need, you tend to grab out of your ERP stack. And then, of course, from userland, how do you get to there? Well, you call this, NT device control file system call. And then if you look at sort of the last 5 arguments are the ones where there's potential for attack surface and where the entry into driver happens, which is your control code, your input buffer length, output buffer length. And so, okay, once that sort of goes through the I/O manager and it goes to your driver, the driver goes to your device control dispatch and sort of packages up this ERP and hands it over. So depending on your I/O control code, the way this data gets packaged up differs. And so let's look at what the I/O control code looks like. Even though it may look like just a number, it's actually split up into several different bits and pieces. From a security perspective, we really only care about two pieces of those, the required access and the transfer type. And so I'll say a little bit about transfer type and the required access. Required access is basically one of three. It says file any, file read data, and file write data. And what that means is if you open a handle to a device and you say, I open it as read-only, and then you issue an IOCTL that requires file write data, for example, the I/O manager sees, your handle is only open for read, but your IOCTL code says file write data. That doesn't match, and so the I/O manager will kick you out. And so this restricts you to the required access that you need. And so the other one is the transfer type, and there's basically 4 different kinds of transfer type. There's the buffered, neither, indirect, and outdirect. And so let me sort of run through those real quickly. The first one is method buffered. And method buffered is sort of the preferred, safe-ish way of passing IOCTLs to drivers. What that means is the I/O manager basically looks at the data that userland passes in, and it says, okay, your input buffer is, I don't know, let's say 10 bytes big. What I'll do is I'll mirror it. I'll create a kernel buffer that's 10 bytes big, and I'll copy your data over. And then I'll pass that on to the driver. And what that means is the driver doesn't have to worry about, race conditions or making sure that the address is within user and doesn't point to kernel, and all these tricks, you don't have to worry about it if you're using method buffered. Additionally, when the kernel does all that copying of data around, it charges quota for your memory. So if you hit your quota, then that fails and it sort of returns and fails. So method buffered is sort of the safe-ish way of passing data around. Method neither is the exact opposite. The I/O manager does nothing. The I/O manager basically takes the data given to it as is and sort of passes it on to your driver. So your input buffer, your input buffer length, your output buffer length, they're just raw pointers or raw lengths that have not been validated and passed along to your driver. This is the endless source of Windows driver bugs. It's in my view, as a driver writer, you should avoid them at all costs. Unfortunately, that doesn't appear. There's plenty of drivers that do this stuff. And I mean, there's a perf benefit, but it's a huge strain on resources for security because you have to manually check everything yourself. So in order to just do sort of describe method indirect, method outdirect, I first have to say something about these things called MDLs. And an MDL is basically, it's called a memory descriptor list, and it's a data structure in the Windows kernel that represents a buffer by its physical address. And I'm not going to discuss because the internals are kind of opaque, but basically Windows kernel has APIs to create, modify, delete, and consume these MDLs so that you can go and say, okay, well, I have this MDL that describes physical buffer. Now give me a kernel virtual address for it, for example. And I think it's the memory manager that'll do it then for you and basically hands you back a pointer. Why is this important? It's important because in this particular case, where the I/O manager passes stuff back and forth, what usually happens is you have this double mapping. So what happens is the user goes to kernel to I/O manager and says, oh, I have this userland pointer and this length. And the I/O manager goes to it and says, okay, I'm going to create an MDL that sees what this userland pointer is and figures out what the physical memory behind it is. And then, if it's more than a page, it finds all the physical memory pages and sort of packages it up in MDL and passes that off to your driver. And then when a driver looks at it, it'll see the MDL and say, okay, now get me the kernel virtual address for it. And so you get sort of double mapping in user and kernel that both map to the same physical page. And the reason why you would do that is so you get these situations where if you have to copy large amounts of data around, because you're using MDLs, you now have zero copy. And so you get a huge, huge perf increase. Essentially, that's, if you draw an MS Paint, that's what it looks like. Yeah, and so this is done for perf, and you get 0 copy. Additionally, you have no pain of probing and try except. And so there are definitely upsides to MDLs. There's also downsides to it, and I'll get to that later. But essentially, now that you have an idea what MDLs are, basically met indirect and met direct are these things where met indirect is sort of the input is going to be an MDL, and so when your driver takes input and starts reading from it, it'll come from an MDL. And when you use met outdirect, it's going to be the exact opposite, where it's like once your driver generates output, you just put it to an MDL, and then user automatically basically gets it. In short, that's what these things are. Okay, so this is sort of my last slide for part 1. So I hope I wasn't too confusing. I know I ran through it really fast, but it's because the next section is really where all the cool stuff is. So most of the stuff I talked about or will talk about is this WDM model, which is older. And so KMDF is this new kernel mode driver framework. And it's part of what's called a WDF, which is the something driver framework. And basically, this thing was made it was designed based upon learned mistakes from the WDM world. A lot of that has to do with power management and things like that. But also for security, a few things became apparent, and it sort of made easier to do and use in KMDF. And so in general, KMDF makes it easier to write drivers and less likely to introduce bugs. But it is layered over the same infrastructure that WDM still uses. That is to say, if you don't understand the old model, you're still going to have sort of these implicit KMDF bugs. But in general, it does make it harder to have bugs. And so one example, security-wise, is a great one, is where it strongly discourages the use of passing user-length pointers directly to kernel. And in fact, so they have these set of APIs to sort of extract data out of the requests. So one of them is WDF request retrieve input buffer. And if you have method buffered or method indirect or method outdirect, that API will just go grab the pointers for you. But if you're using method neither, that API will totally fail. And if you must use method neither, then you have to call this new API called WDF request retrieve unsafe user input buffer. And that, pretty explicitly tells you that it's unsafe. And so it's one of these things where, they really knew that using these method neither things are horrible, and so they made it really hard for you to use it. And so if you do use it, the names very explicitly tell you that things are unsafe. And generally as a driver developer, you're encouraged to use KMDF over WDM. And the cool thing about KMDF is that it's actually open sourced. Earlier this year, Microsoft slapped an MIT license on it and put it on GitHub. And about 90% of that code is there. There's tiny bits and pieces still missing. The redirector isn't there yet. But by and large, the guts of KMDF are totally available under a free software license, I guess. And if you want, you can totally take a look at them. Okay. So now that we got that out of the way, let's dive into the what of Windows drivers attack surface. So basically, by and large, when you look at the sort of bugs you have in a driver, there's sort of three things that come up, right? They can be elevation of privilege bugs, like a buffer overflow or something like it. They can be denial of service, right, where you get a kernel panic or a deadlock or resource starvation type of attacks. And the third one is where you get information leaks, right? By and large, those are the ones you would see when you look for security implementation bugs in drivers. And so that's sort of by and large, the kind of things that I'll talk about. Specifically, things that I'm not covering are exploitation or bypassing of mitigations. For the most part, there's bits and pieces where I'll sort of mention some of that. But by and large, I'm working from the assumption that bugs are going to be exploitable. If that's not what you're looking for, this isn't an exploitation talk, which is what I pretty much start off with saying. So I won't be focusing on exploitation. I will instead be focusing on sort of identifying these type of bugs and developer guidance on how to fix those kind of issues. The other thing is that I'm assuming that you guys have a basic understanding of, native code security. So I won't discuss, the standard buffer overflow or integer overflow or, what it means if you have an unvalidated length field. I'm assuming those things are understood. Same thing for, C++ type of bugs or those kind of things. So just because I said I wasn't going to cover integer overflows, I lied. I am actually going to say something about them. Specifically because in the Windows kernel, you actually have these APIs to help you not have integer overflows. They'll have a set of APIs you can use. And if you are a driver developer, you are encouraged to use them, even though I haven't seen them all that often. And you should, in fact, use them. But when you use these APIs, you should sort of, there is still potential for misuse. And basically, when you use the APIs, there's sort of the three things you should always or never do is always check your return value, always pass in the exact type, and always never do arithmetic when passing parameters. Because when you do any of those three things, you're basically sort of reintroducing your integer issues when you're trying to use these new APIs. And I have examples of this stuff, but in the interest of time, I'm sort of just going to run through it really fast. Basically, the stuff on the left is wrong, and the stuff on the right is correct. So the stuff on the left is sort of here's how to use the APIs wrong, and here's how to use the correct use of the APIs. Okay, so basically now I come down to sort of, what I did is I sort of sat down and sort of, looked over, what the most common security bugs are in drivers and sort of tried to figure out what's the common theme around all of these. And I came up with this idea where there's 5 things that most drivers will do if they're talking to user land, where there's potential for attack surface and where you have some kind of entry point. And basically, it comes down to when you create a device, when you talk to the I/O manager, when you handle data, when you interact with the memory manager, and when you interact with the object manager. By and large, those 5 areas, a driver will, if they talk to user, those are the 5 big areas where you have attack surface. I mean, it's not, there can be other ways too, but by and large, my view, it's those 5. And so basically, I sort of structured my next set of slides around these 5 areas, and then for each one of these 5, basically, I'll discuss a few things that I've seen gone wrong and so I'll have the first set of slides, and I'll have a cute little icon on the left top that indicates this is a bug, and then a cute little icon with some tools that says this is a fix. But by and large, I go by these 5, and then for each one of these 5, there's a couple of cases that I cover. So with that, let's start with device creation, right? As I showed earlier in the sample driver is when you create a device, you basically have this API call, which is IO create device or IO create device secure, and your driver basically goes to the IO manager and says, please create a device for me. When you do that, you can say, okay, these are the access controls that I want on it. And there's 2 ways of doing that, right? One is you call IO create device secure, and you can pass around this what's called SCDL string, which is a string representation of a security descriptor, which basically says who can and can't access the device under what conditions. If you don't call IO create device, the other way to do it is you specify the SCDL string in the INF file that comes with your driver. And then that will be applied by your manager when somebody tries to connect to your device. Commonly, though, these things are missing. You'll see a lot of drivers that they'll call just IO create device, and they won't specify an SCDL string in INF. So you fall back to either default or sort of an ACL that's too wide. This is just a common sort of simple design problem that you see with drivers that are thrown together too fast. Basically, the idea is that you just sit down and sort of try to figure out who needs access to your device and under what circumstances. And I mean, it has value to sit down and really think about this, because what you're doing is you can try to reduce kernel attack surface, right? And so one good, proper engineering example would be to sort of sit down and say, okay, well, we have these set of ioctls that really an admin should only ever need to do. So what we're going to do is we'll create a driver that is only accessible by an admin, and then what we'll do is we'll create a service on top of that that you can then talk to through, I don't know, UDP or RPC or whatever, and then they have the service sort of reroute things to the kernel only when it needs to. So in that example, the downside of that is that you have to write more code and you may get some performance degradation, but the upside is you get extra security and probably better reliability as well. So that's one solution. But the idea is basically that this is usually a design question where it's like, okay, who really needs access to our device and why, right? Okay, so with that said, let's move on to some more implementation stuff for device creation. When you create this device, you call this IO create device API, and basically you're allowed to pass these device characteristics into it. And basically there's one bit in there, which is this thing called file device secure open. And it has very special meaning. So basically, when you create a device in the Windows kernel, by default, the IO manager will always assume that it is a file system device. And what that means is that when you open a device, the IO manager basically assumes that it has directories and files. And so if you do, instead of you open device, you say device/file, the IO manager looks at it and says, oh, I don't have to apply the ACLs here. The file system has to do it. I'll just go to the file system device and let the file system device handle it. And that works really well if you're a file system driver. But if you're not a file system driver, which most drivers are, so if you're not a file system driver, all of a sudden you have this problem where the IO manager thinks you are, and it won't apply your ACLs, and then hands it off to you, but you're not checking your meter, and so all of a sudden, if you don't set this particular flag and you're not a file system driver, you have this sort of by design automatic ACL bypass problem. And so that's why pretty much every time you create a driver and you're not a file system driver, you should really, really set this flag. And it's bizarre because it's actually documented, and there's a lot of drivers that are not doing this. And what's really funny is that this bug is incredibly easy to find. There's a tool out there called Device Tree, and it enumerates all of your devices, and you click on it, and it'll allow you, it's kind of hard to see there, but you can basically see what the ACLs are, and then it also says whether this file device secure flag is set. And so if the flag isn't set, and the ACLs basically say, oh, this is only admin, then you most likely have a security bug right there, and it's one click away. It's easy to find. So what's the fix for this one? Basically, always use the flag. Unless you are very specifically building a file system driver, you should always set this flag. That's the general rule. Now, some people go, well, you don't have to set this flag. You can sort of make your own, create a dispatch callback and sort of do it in there. And yes, you absolutely can. You probably shouldn't because A, you're now adding more attack surface even though this functionality is already there in the Windows kernel. Just set that one bit and you get it for free. Two is, if you do it yourself, there's a few intricate sort of little things that you want to try and mimic exactly what the IO manager does in that case. Otherwise, you get these sort of discrepancies. So yes, you can't do that, but unless you're doing a file system driver, probably shouldn't. Okay, so that's one of 5. So the second of the 5 I had is basically working with the IO manager. And the first case I had is sort of a simple one, but this is a pretty common one I've seen in a bunch of drivers where basically you'll have some like ioctl callback, and it'll be method indirect or method out direct. And it'll say, okay, well, we'll use the ERP MDL address and we'll sort of get do the get system address for MDL safe, and we get our kernel pointer out of it, all without ever checking if that pointer can be null. It can be null by sheer the fact that the way it works is that pointer can absolutely be null. And so before you ever touch our ERP MDL address, you should check it for being a null pointer. And this one of the cases where it can happen is if it's a zero-sized buffer. If you're not doing that, then you may very well have a bug check or worse, and I'll talk about that later. But the idea is that if you're doing in MetaDirect, check your MDL address before you use it, which is also fixed. Great. So the second sort of problem-ish in the IO Manager class is using MetaBuffered. I discussed MetaBuffered before, and I said it is the sort of safer option, and it is. But there's still some things you should know. Is similar with the MDL address is that the pointer you are given from the driver spectrum in the ERP for MetaBuffered is this ERP system buffer, and the problem is similar to the MDL address where that pointer can also be null. So the first thing you should do is always check, make sure it's not null. The other thing with MetaBuffered is that even though it is the safer, or I guess the safest method of all four, is that because it's seen that way, you get this sort of false sense of security. In that, while probing and capturing of the whole buffer happens for you, any and all of the content inside of that buffer still needs, depending on what it is, still needs any kind of validation, right? And so there's a set of developers that'll say, "Oh, MetaBuffered, cool, we're good. We don't need to do any security checking." And then they'll have some kind of embedded linked fields that are never validated and used to copy stuff around, and all of a sudden you get memory corruptions left and right. So yeah, the idea with MetaBuffered is that A, validate for null, and B, all the embedded content still has to be validated. One of my all-time sort of pet peeves or kernel bugs is this. Basically, let's say you get an ioctl, and you do all the work and everything, and you're successful, and the ioctl is completed correctly, and you're about to sort of return. And you basically, there's a field in your ERP that says IO status, and you basically say, okay, IO status success, and then there's this thing called IO status information, and the information it's basically an integer. And in the case of success, what that means is I have completed successfully, and these are the amount of bytes that I give to you as output. Basically, quite often what people will do is they'll go to IO status.information. They'll say, okay, whatever output buffer length that the user gave me, that's the number I give you. And sure enough, you do that, and everything works. Nothing crashes. You get all the data you need, and everything works perfectly. But there's this very subtle thing where basically all of a sudden you have this information leak. So basically what happens is when you do an ioctl and you go to the IO Manager and you have MetaBuffered, the IO Manager looks at your input length and your output length, and it says, okay, which one of these two is the maximum? And it says, okay, let's say the output length is the bigger one. It goes and says, okay, malloc of kernel buffer of that amount of data. And then it sees what is the length of the input buffer? And it says, oh, the input buffer is X, great. We'll take the input buffer and we'll use that length and we'll copy it into this buffer I just located. So if you have an input buffer that is smaller than the output buffer, then the delta between input and output is uninitialized memory. And if you now have this bug where at the end of you're done all the way at the end, and what you've copied into the output buffer is smaller than the total allocated space that is available, then that delta all the way at the end is uninitialized memory. And so if you then go and say, IO status dot information is the full buffer length, then that includes that piece of uninitialized data all the way at the end. And that gets copied back to userland, and then when userland gets the buffer, they can just read that stuff. It's kind of subtle because stuff doesn't crash, stuff doesn't break. You have to really look for it. But quite often, when you have these kind of bugs, is you can rig this so you get really large buffers. You can say, I want a 1 or 2 gig buffer, and all of a sudden you get just piles and piles and piles of uninitialized data that comes out of kernel and contains all sorts of interesting things. And so this is, I reversed out of a driver, but it's a fairly common bug to see because you can test all you want, this thing will never crash. It's kind of subtle. So unless you know about this bug explicitly, people don't find it either in testing or for looking for security bugs. But it's basically the common cases where you start your dispatch routine, you say, okay, this is the output buffer length user gave me, and then you do all the work, and then all the way at the end when you're done, you say, okay, IO status information is, we start off with the output buffer length, and boof, off we go, and all of a sudden this thing just leaked information. The other thing that's really interesting about this one is, even though this is a WDM thing, and even though KMDF is sort of built on top of this, in KMDF, you can still have this particular mistake. You don't actually manually fill out the members of the ERP, but KMDF gives you a set of APIs to do it, where you basically just pass parameters. So it's a WDF request complete with information, WDF request set information. Both of them fill out this IO status field, and if it's too large, you have the same problem. And because KMDF is open source, you can just go look at source and see what these functions do. And indeed, if you look it up and you see what these functions do, you'll see that internally they still look up the ERP and they go and say, IO status dot information, and the length you give it. The fix here is simple. I mean, it's a little bit hard to figure out initially because the bug itself is so subtle that, because nothing crashes, nothing ever misbehaves, it's kind of subtle that way. But once you're aware of it, the bug's really easy and it's incredibly easy to fix. Basically, anytime you set the information, you should just be exact. If you copy 5 bytes in there, then say that, right? Always record the amount of bytes you put in there and then just make that your IO status on information, and you never have that bug again. The thing is, though, you have to be consistent about it, and that can be pretty hard, especially if you're reviewing old code. And so it's really easy to miss 1 or 2 cases that is still lying around, code that was written 20 years ago. Okay, so the last part about the IO Manager that I want to talk about, and this is sort of in broad strokes, is about ERP cancellation. And the reason why I talk about it broadly and not specifically is because it's incredibly complex stuff, and I could easily fill a 1-hour lecture just about ERP cancellation stuff. So basically, what happens is when userland does an ioctl and it comes to the driver, and the driver says, okay, well, this is an ioctl that I can't complete right away, and so what I'm going to do is I'm going to go take this ERP and pend it, and I'm going to go back to userland and say, hey, come back later, or I'll give you a signal later once I'm done. You can go do something else now. And then once the driver is done, it says, okay, well, this ERP is now completed. And then it signals userland and says, hey, I'm done. The time in between is undefined, depending on what the driver is supposed to do. Can possibly be a long time. For example, something that's disk-based. And so basically, at any point after the ERP is pended and userland knows that the kernel sort of pended it and is working on it, userland can go back to the kernel and say, oh, hey, that driver that's holding my ERP, I'm done waiting. You've taken way too long. Just cancel the damn ERP. And then basically, the driver sort of gets woken up again and finds your ERP and cancels it. And the problem with this is that there's this potential for all these race conditions, right? Where you'll have one thread that's still trying to work on the ERP, and you'll have another thread that has been instructed to cancel it. And so you have one guy working on it and one guy canceling it. And if they're not in perfect sync, you have all sort of these weird race conditions. And so that stuff gets incredibly complicated. And so there are literally dozens and dozens of examples of what the stuff looks like, and I wish I could get into it, but I can't. But I will say, though, that ERP cancellation routines that have synchronization issues often lead to deadlocks, memory leaks, race conditions, double freeze, and use after freeze. So all the stuff that, if you're a security guy looking for bugs that you start drooling when you hear those things, they're all in there. And I really wish I could get into detail. And so fix-wise, it's there is no easy advice to give. This stuff is just extremely complex. And sort of when you do ERP cancellation, be very careful, be extremely conservative. Implement with care. You know, double check, triple check, have it peer review, check again. You know, try to use cancel safe ERP queues. That's pretty much it. Unfortunately, there's no better advice. Okay, so now that we've got those two down, let's move on to userland and data pointers. And so I guess we should first talk about the elephant in the room, which is basically, you know, what if a driver takes, you know, direct pointers from userland? What you're supposed to do these things called, you know, probing, which is basically, you know, a fancy word for is this pointer within the range that userland is allowed to be, and including the length and then the end pointer, and does it not overflow and all those things. And that's basically what the probe for read and probe for write functions do. Okay, there we go. So basically, you know, if your driver takes pointers from userland, you're supposed to do this kind of probing. If you don't probe, so let's say you take a pointer from userland and you forget to probe, and you read from it, basically that's potentially information leak. You could be reading from anywhere, and you could definitely crash. And depending if that information gets sent back to userland, you could potentially info leak. So that's bad. But if you get a pointer from userland and you don't probe and you write from it, you basically get this sort of a write anything anywhere primitive in kernel, and that is extremely bad. You basically just own the kernel if you're doing that. And so basically, to try to prevent these cases, you do probing and use the probe for read and probe for write APIs. And so this is one example. I think this is some Intel driver, where basically, you know, you take an input buffer and then basically there's no probing anywhere in between, and you just sort of read and write from it. But suffice to say, these bugs, unfortunately, are extremely, extremely common. Another interesting sort of nugget with this stuff is that, and this, I think this was noted a few years ago, is that, so these probe APIs, basically the way they work is you say, okay, here's my userland pointer, here's the length I want you to probe for, and here's the alignment. And you can have these very subtle bugs where people do probe, but for whatever reason, the length given to the probing is 0. And Windows APIs basically go, those probe APIs basically say, okay, well, if the length is 0, short circuit logic, return success. And that is perfectly valid. You know, if I say a probe of 0, then I mean, you know, clearly that's 0. The thing is that there's a little bit of risk here when that's being done. Basically, the idea is that if you probe with a length of 0, and then later on you basically use that address, but then you read or write 1 byte. Obviously, the bug there is that you have a length discrepancy between 0 and 1. But the difference is that because the way the probe APIs work, this length discrepancy becomes incredibly exploitable, right? If the probe APIs had worked a way where they said, okay, well, the length is 0, what we're going to do is we're just going to make the length 1, and we'll just probe that particular address, it would make these bugs far less exploitable. And so that's why there's risk here. The common case for where these kind of bugs can happen, where you do have a probe with length of 0, is you'll see this code where they'll take like an input buffer length, an input buffer, and they'll just assume it's of a certain length, and they never actually double check what the length really is, but they still pass the original input buffer length to the probe functions. And so if you forget that kind of length check, you end up with these exact kind of issues. The other one is where if you do length checks, is that you may still have like length integer overflows, where the probing length just happens to overflow right back to 0. So that can happen too. So the fix basically is perform correct, consistent probing. Always, always, always probe. It's easier than it looks. You always forget 1 somewhere. It's one of these things where once you start, like if it's all in one simple function, then that tends to be easy. But you'll have these things where you have these complex drivers where it calls a function that calls a function that calls a function, and somewhere down the road you're not quite sure if it's a user pointer or a kernel pointer. And then you end up missing a probe. So the second sort of variation of this is, okay, let's say you take a kernel pointer, you take a user pointer in kernel in your driver, and you've now probed it, and then you're going to start using it. You can still do things that are horribly wrong. So every time you use a pointer, a userland pointer in kernel, even after it's probed, is that you must always wrap this in a try except. The reason being is that if you don't do it in a try except, is that after it's been probed, you could have a second userland thread that takes your mapped address and basically changes the page protections or unmaps them. And then somewhere in kernel, after the probing, they go, oh, we'll just use these pointers. And all of a sudden, they're reading or writing to unmapped pages, which will throw an exception. And so that's why you must always do a try except. And so the obvious case is to forget exception handling. But in the less obvious case is maybe you do have a try except case, but the thing is the except case is rarely exercised because it's the exception, right? It almost never happens, and as such these bugs in exception handlers often don't show up in testing simply because it's never been exercised, and so. Even if you do try except with userland pointers, it's still quite often to notice things like memory leaks and reference count leaks. So the fix here basically is A, use try except when using userland pointer, and B is make sure your exception logic is sane. Exception logic can be really tricky, and so you want to design and implement that stuff with care. Okay, another bug related to userland pointers is they're called double fetches. So the idea basically is I'm userland, I go call into a driver and I say, okay, here's the userland pointer. And the driver takes the pointer and it does the probing and it does a try except and it does all that stuff right. But it'll take a pointer and it'll say, let's say it contains an embedded length field. And what they'll do is they'll dereference the userland pointer and they'll make sure that length field is valid. It's got to be, let's say, I don't know, bigger than 10 and smaller than 100 or something. And then sure enough, that's true. And then right after that, they'll dereference that pointer again. They'll take the length field and they'll use it to do something else. And the difference is that there's a race condition here, where basically between the first check and the second check, because I could have a second userland thread that basically overwrites that memory so that when you check it, it's okay, and then when you start using it, it's some totally different value. And this is a simple example of what that could look like, where basically you'll have some function in kernel where you pass it some user pointer, and user pointer will contain some embedded length field. So in this case, it's got to be smaller than 100, and then they use that length field to copy into a local stack buffer that's 100 bytes. And so between that check in read the first time and the use on the copy memory, you can have a second userland thread that overwrites the length. And basically, you end up with memory corruption. And this is an example of a bug that is a double and triple fetch that I found in the F-Secure AV program a couple of months ago. And I have a link to the advisory below if you want to look at it. The fix for this kind of stuff is basically capture data, validate, and only then do you use. Never fetch again. Keep the data you captured and validate that and use that. Similarly, for userland type stuff is basically it's sort of null dereferences. I consider that in the same class. It's not specific to Windows drivers. I actually spoke about this particular bug at the CC conference here in 2006. I was talking about the Linux kernel at the time, but it applies just as well to the Windows kernel. And basically, the only difference is in trying to trigger mapping the null page is in Linux and Unix. You basically do mmap and you say fixed and you just give it an address of null and it'll go map it. In Windows, it's slightly more tricky, where basically, if you try and map the address null, it basically sort of goes like, oh, null means you don't mean an address, well, it's located for you. And so the way you're supposed to do it is you say, no, the address is 1, and then what it does is it rounds down to 1 to a 0, and then it goes and maps the null page. But it's essentially the same thing. This used to be a much bigger deal. As of Windows 8, mappings of the null page are disallowed. which isn't. So that's what they'll tell you, and it isn't entirely accurate. On 64-bit Windows, mappings of the null page are disallowed. On 32-bit Windows, mappings of the null page are disallowed by default. But there's this thing called the NTVDM, which is the virtual DOS machine. So if you want to run old DOS games, for example, you have to turn this stuff on, and all of a sudden you can have null pointer references in your old DOS games, and those would then allow you to exploit null pointer references in Windows drivers. Essentially. But even if in this if this sort of little corner case doesn't work, and we take the premise that null mappings aren't allowed in Windows as of Windows 8, there are still some exceptions where null pointers in kernel might be exploitable. So one is if you have null plus a large offset, where the offset basically becomes your pointer. A common case of this might be where you have a memcopy, a reverse memcopy, or where you pass null to a function that has a special meaning. Yeah, the fix is basically defensive programming, right? I mean, we all know about null pointer references. They're nothing special. Okay, I'm just going to skip this because I'm running out of time. Okay, so memory-related bugs. This is number 4 out of the 5 I had. Basically, if you're a Windows driver, there's 2 set of APIs you do to allocate memory. It's the allocate pool and allocate pool with quota. And basically, there's a discrepancy between the two where one of the APIs, when it fails, returns null, and the other API, when it fails, throws an exception. So if you mix up one with the other, all of a sudden, you're checking for a return value, but you might get an exception. Or you have an exception handler, but what really happens is you get a null pointer back. So you have to get those straight. And I believe one of the pool with quota actually allows you, it has an option where you basically go to it and say, hey, instead of throwing, give me a null. I would recommend using the API that way because then you have consistency. But that's one of the ways you can go wrong using these APIs. There are 2 other things. One is basically, so the allocate pool with quota is basically done so that anytime you do an allocation in kernel driven by userland, you're supposed to do allocations based on the quota of the userland caller, right? So in my view, anytime you do an alloc based upon driven by userland, you should always do the quota alloc. If you don't, I think that's a bug. And then, of course, the other are simple case, right? Whereas obviously, yes, if you don't check return value, yes, you may have null dereferences. If you don't handle exceptions, yes, you may have unhandled exceptions. And even if you are, you can have faulty exception logic. These are pretty simple, fix-wise. It's like, yes, check return values. Yes, charge quota when you have to. Yes, cap buffers, please. Don't have unbounded allocs. So the second sort of memory-related issue, and this is new as of Windows 8, and this is mostly a mitigation type thing. So by default in Windows, when you used to do a memory allocation, the pages you would get back were executable. As of Windows 8, that is no longer true. So there's a page pool and non-page pool. For the page pool, by default, they are now not executable. For the non-page pool, they still have to be. And so they came up with this new thing called a non-page pool not executable. And the idea is that anytime you do a non-page pool alloc nowadays, is that you specify this particular pool, the non-page pool NX, unless you really need executable non-page pool memory, which is not impossible, but it's pretty rare that you actually need it to also be executable. And in that case, sure, go ahead and use the non-page pool one. But in any other case where you need non-page pool memory and you don't need it to be executable, you should really use this flag. It's not a bug per se by itself. It's really sort of, this non-executable non-page pool is really mitigation for exploitation. And so the idea is that if you use this incorrectly, you're kind of killing a mitigation. And so basically the idea is that, let me go back. The idea basically is that you use the non-page pool NX if you're going to do, if you're going to do non-page pool executable. allocations. So the next memory-related bug, sort of there's this API called get_system_address for MDL, which is basically if you get an MDL, how do you get it mapped in your virtual address space or kernel? This old API basically, if you call it, there's the risk of if it can't map it, what it does is it causes a kernel panic. And so there's a new API called get_system_address for MDL safe. And that one doesn't cause a kernel panic. And so obviously you should use a new one. If you see the old one, that's a bug. And while this seems easy, there's still a fair amount of drivers that use the old API. And I started thinking about it, and I think, I mean, there's two reasons why you would still have that. A, if you have an old code base. But I think B is if you're developing based upon driver books and basically books that basically tell you to use the old API because the book was written before new API existed. And there's plenty, most of these kernel driver books are relatively old. And so they advise using that API. And I think that's why these bugs are still around. Yeah, so this is basically what I was talking about earlier, right? Where when you have these MDLs that are used to create a double mapping between user and kernel, all of a sudden you end up with these double fetches again, right? Where let's say you have like an IRCL that comes in with method indirect, and you take it, you get your kernel pointer out of the MDL, and you just start using like embedded length fields, then not realizing that memory can be changed any given time by a userland thread, so you end up with all of these sort of double fetch bugs again. The thing is, they're not quite as obvious as the ones that are directly from the ones I showed earlier, because you're dealing with a kernel pointer. So if you just look at the pointer, you would assume that userland doesn't really have direct control over it. And so that's why they're not as obvious. This is a very simple sort of example of what that would look like, right? So you have an MDL, and you say, okay, it gets the method for MDL safe, and then you get your data back, and then you say embedded length, and then you kind of go, okay, we'll use that embedded length. But because it comes from an MDL, you can have a second userland thread that just changes your embedded length after validation, but before use. Okay. I'm going to skip over this because I'm really close to running out of time. So I think I have 2 more minutes. Sweet. Let me get to the fifth part, object handling, where basically, so when user talks to kernel and it basically says, okay, here's some handle to some file, go do something with it. The way the kernel goes says, okay, well, I'm supposed to, how do I translate this handle to a kernel pointer I can use? You call this function called reference object by handle, and that basically translates one to the other. And the API looks like this, and it has this thing called object type and access mode. And basically, object type says enforce that the handle is of this particular type. And Windows has about 40-something different types of objects. And so if you take a handle from user and kernel and use this API, and you say object type is null, there's no type enforced, and you get all of these classic type confusion bugs. So that's one. 2, the second bug you can have here is basically where if the access mode, you're supposed to specify user. If you specify kernel, then all of a sudden userland gets to give you handles that are really kernel handles. And so because handle numbers are really not secrets, they're easy to brute force. And all of a sudden, if you say access mode is kernel mode, user all of a sudden gets to tinker with your kernel handles. Okay. Another thing with this kind of object stuff is that once you dereference it and you're done, you're supposed to dereference it, and then you're done with handle. And so quite often you'll have these bugs where basically, like let's say you have some kind of exception that gets thrown, and you forget to deref a handle, and all of a sudden this handle leaks. So this is a known sort of ref counting bug. Except the problem with this is if this is repeatable. Let's say your ref count is 32 bits. If you can repeat this about 4 billion times, your ref count overflows to 0, and all of a sudden you have Awesome, perfect. So if your ref count in overflows, all of a sudden it goes to 0, your object gets freed, but you may still have a reference to it, and all of a sudden you get these use after free cases. As of, I think, Windows 8, there has been code added to the ob reference calls, where basically they detect an integer overflow. When an integer overflow happens, they cause a kernel panic. And so all of a sudden these bugs are no longer exploitable beyond a leak, which is great. But up to Win 7, that was still a problem. Related issues are a double ref count increase, use after ob reference, and a passing of null. And the fix is basically always balance your reference calls. And I'm done.
Well, unfortunately, we do not have time for questions.